Hi, so I'm gonna go over how to use our terrain generation combo software, which includes both the Diamond-Square and Perlin Noise terrain generation methods. So by simply hitting the play button, you start off with some default values, which by hitting the render button, you're able to generate a map based off of these parameters. Each time you hit the render button, you'll be generating a new map, and then you're also given multiple parameters which you're able to change either by slider or by simply inputting the value that you want. You're also able to hit the turn the coloring of the mesh on and off, as you can see. So let's turn that back on. Just to do a bit of experimentation with the values, uh, you have three UI values that you're able to work with. Uh, the height values, which you can see when uh, brought to higher values, you get much more or sharper points generated upon the terrain. If you bring them back down, then the generations won't be as steep. You can also work with the sizing parameter, which will make the divisions square size much larger. So something I also forgot to note is so what's in the bottom left-hand corner, where you're able to use the mouse scroll wheel to move around along with WASD for camera movement, and then using the mouse left button to for mouse rotations. So here we have a few different examples of changing size. So if I bring this back down, you'll see that the map will shrink down to something a bit smaller. And then if we bring it all the way back up, then you'll once again get a much larger terrain. And then the last parameter which you're able to work with on the Diamond-Square terrain generator is the divisions. This is essentially the number of vertices along each parameter. So there are 128 squares upon each border used to generate this terrain. So if you drop this down to something a bit smaller, let's do something just like 8, uh, you'll see that the texturing is not as defined, but you're able to see that the number of squares has decreased to that value. But usually you'll want to go and stick around higher values as it will allow for more defined terrain generations. So the other side of the application that I want to show is the Perlin Noise terrain generator, which you can access from the drop-down located in the top right by simply opening and then hitting the Perlin Noise. And then you can switch between these two, again, just simply by using the drop-down menu. And as you open up the Perlin Noise generator, you'll be given a new set of parameters that you can use to manipulate the terrain. This works slightly differently from the Diamond-Square generator, as rather than having a render button, the changes you make will actively be auto updated to the noise map, which is then translated automatically to the mesh map. So you're given 7 different parameters. The first one I want to go over is the offset, which is pretty simple, of just the x and the y coordinates. You're able to use these offset values to scrub through the noise map, as you can kind of see, depending on the combinations used on the offset, you're able to scrub through and explore the noise map rather than having to completely regenerate new new values every time you load the program. Uh, if you want to change the generation of the maps, you can go into the seeds, in which it would have to be done outside of runtime, and you can change the seed used for the randomization generation. Uh, but to go back to the other five uh, parameters that you're able to change. These impact different values used for uh, creating the noise maps, which are combined to create the overarching Perlin noise map, which is shown on the right side of the map. So first you have the scale method at the top, which as you see kind of lets you zoom in and out of the noise map uh, as such. The next is the height map. Let me get down a bit lower and you can see this is a multiplier which will basically make the uh, heights go higher and lower depending on however you want. If you drop it all the way down to 0, you'll be able to see the direct translation of the noise map to the texture map used. So as you can kind of see, there are some black spots here, which translate to the deepest points of these watermarks. So let me raise these back up a bit. The next is the octaves. This is probably one of the most important as it works with the layering used for generating these noise meshes. So let's get to 5 on this side. Then these last two, the persistence and the lacunarity parameters are used for increasing and changing the ratios uh, used for manipulating the amplitude and frequency values, uh, which help to generate these noise maps. So as you can see, when the lacunarity increases, uh, it gets a bit more pixelated. So let's drop that back down to something a bit lower. And then with persistence, you'll see you'll start getting something sort of similar, uh, but will basically change the frequency of uh, the values within the noise maps. And then the octaves are, of course, used to define the number of layers used when combining these values together to create the overarching Perlin noise map. So yeah, that is all it is for the user guide. Now we'll go over some of the scripting of how each of the methods were built.
Hi, this is Hwanjoon Jang and I'll explain how to make Diamond-Square method. To generate 3D terrain using a Diamond-Square algorithm, it's necessary to first set up variables. These include the number of divisions in the terrain, the overall size, and the amount of height variations. At first, I put the divisions for 128 and then size for 6 and height for 1. After that, the code sets up a variable try_offset to track the current position in the triangle index array. This part is in our script, and then that creates loops to iterate over each point in the grid using a double for loop based on division. To add randomness and height variations to the terrain, the code assigned the random height to the corner points of the terrain. It also calculates the number of terrain based on the number of terrain division. Through 3 nested for loops, heights are set for the center and corners of each square, and the diamond square function is applied to each square. This part is in here. There is three nested for loops, and then the diamond square function will work in here. The diamond square function is a crucial part of the algorithm. It calculates the indices for the top left and bottom left vertices of the square, and then the index for the square center. The height of the midpoint is determined by averaging the heights of the square's four cornered vertices and adding a random offset known as a diamond step. That is this part. Next, it calculates the heights of the midpoint on each edge of the square. Each edge midpoint height is set using the average heights of adjacent vertices and the random offset referred to as a square step. Square step part is this part. Repeating this process across the entire grid adjusts the vertices height iteratively, adding diversity to the map. This combination of averaging and random offset at various scales create a fractal-like appearance in the terrain.
Hi, my name is Nathan Thomas-Benke, and I'm going to be going over a kind of brief overview of the scripting used to create this Perlin noise generator. So there are three different main steps used for creating this. The first step was just creating the noise map. So if you see on the right, just by entering noise map into this map generator script, it creates the noise map. So if we go into the code here, you'll see this is kind of just where all those parameters were set. Here are the sliders used in the UI. Basically, the update, how it's being done during runtime, or it's being run on runtime, is it's basically just constantly updating the values from the slider, and then it's constantly redrawing the noise map and then the generate map function. Uh, just to quickly go over, the generate function is basically creating the noise map, which is calling the Perlin noise function, which we'll go over in a second. It's creating the texture map. Then it's kind of going pixel by pixel. It's mapping the height, and then in this for loop, it's going and defining each pixel as a certain texture value depending on the height and the region defined in here. Uh, then after that, it's basically sensing what draw mode is selected, and then it's either displaying or drawing the texture onto the plane. Whether it's a noise map, it's drawing the texture map, which you can see if you select texture, then it just redraws it here, which is the same as the mesh if it's just zeroed out, and then finally the mesh generator, which also I'll go over later. This is just a quick validation script used for making sure that the values aren't or that it won't cause any issues when it's being generated runtime. As you can see, the program isn't running, but it's still being updated as you kind of change the values. I guess I need to go to the mesh, don't I, to change that? Yeah, there we go. Okay. And then the final thing in the map generator here is just kind of the the region elements for the textures, which were kind of shown here, where it's just the string name, the height, and then the actual color associated with the region used for painting. Now I want to go over to the Perlin noise. So this is what actually creates that noise map. Uh, so it takes in multiple parameters such as the map width and height, which need to be uh, the same. Usually I just have it set as 100. Then these are some of the parameters that you're able to change: the scale factor, octaves, persistence, linearity, and then the offset, which is X and Y. And then there's also a seed used for creating the randomizations. Then just kind of to quickly scroll through, you can see this is setting up the offset logic. This is working to make sure that the scale factor doesn't hit or isn't negative, as that causes issues. Then this is the main logic used for uh, finding the correct values for uh, the Perlin noise map using the varying uh, frequency, offset, and then scale factors along with the center maps. Uh, and basically, again, it does this for each pixel. It calculates the X and Y values for each of them, and then using the Perlin noise function built into Unity, it's able to get that Perlin value, which is then set as that noise map. And then the height, which is actually used later in the mesh, is multiplied by the amplitude. Then you have the multipliers for the persistence and linearity. Persistence is usually between 0 and 1 as a ratio, which is why it decreases, and then linearity is usually above 1, which is why it increases. And then this is again just kind of getting the maximum, min, and end max noise values, which were set above. And then, yeah, just at the bottom, it sets the height during each loop through. And then this also just normalizes the values, helps make it so that there aren't just any crazy outliers, and then make sure that, as said here, the it's below 0 and above, or the max of 1. So it just makes the noise map of the early state, the height during when the mesh generator is run, look a bit better. Here in the texture display, there's just a quick few functions where this is the draw texture or this is used for creating or drawing on the plane object, and then the draw mesh is used for drawing onto the mesh object. Here in the texture generator, these are use two different inputs. This is uses the texture map. It create or this these are two functions that just make the map look a bit nicer. Where it's either that there was some overlap where I guess I can quickly show, hopefully. If I close those and do texture map and then remap, you can see the lines get a bit more blurry, and then also there is some, you can kind of see the pixels on the borders uh, whenever you don't have these lines defined. That sets the pixels. And then this one does essentially the same thing, but this is what's used for the height map. And then finally, the most important one is the mesh generator. So this is kind of taking in, or it's using the values generated from the Perlin noise map, as well as the texture map as seen here, where it takes, it maps the color map, and then also the noise map. along with the mesh multiplier and multi-curve, which are at the bottom, which so this is the mesh parameter, and then this is also for the smooth step, which I'll mention in the paper. It just makes the height values connect better, essentially, to simplify it. But here, this is basically uh, calculates the mesh data for each of the triangles, and it correctly uh, evaluates the difference of for each pixel defined. Let's see very easily. Yeah. So as you can see, each there it's the mesh is built up of, I believe it's 100 pixels across. So this basically maps each triangle to the correct values while correctly uh, taking in the values by the noise map. So it takes the height map, which is the renamed from the as the noise map, and then it takes the width height values to uh, map the triangles to the correct values, and then this is just kind of uh, quick defining values for creating the mesh that we're defining the vertices, the triangles are for the A, B, and C for the squares and the mesh. So that's kind of a quick, uh, not super in-depth overview of how this map generator function was created.